Okay. The silicidation is a process that is it clearly shown here? Yeah. When you form a silicide, the way to do this is you already have a source and a drain and a gate, something like this, okay? And then you are going to have contact holes by form interlayer dielectrics like this. And you're supposed to form a silicide just on top of this silicon surface, okay? Something like this. Okay. Normally, what you have to do is you have to deposit a metal film, trench a metal film, after you form things like this. Okay, this is, let's say, suppose this is a silicon oxide or something, and then you deposit the metals, trench of metals, and then you etch those things to get a patterns to cover this contact holes only, and then you put that specimen into the furnace, like a 900 degrees centigrade or so, to form the reactions to form a silicide. Okay, but in a silicide, what you do is silicide. This is a self-aligned silicidation. You do not do the lithography after the metal deposition. Some of the materials, platinum, and that has been listed here. This silicide is not available for other elements but platinum, cobalt, nickel, palladium, titanium. Only these 5 elements can do that, the silicidation process. And in the silicidation process, you just cover up those metals on top of this whole thing, and then you do not do the lithography. You just put as it is into the furnace at the 950 or 900 degrees centigrade. Then those elements, only that the 5 elements, is reacting with the silicon only, okay? And then the metal film, which is deposited on the ILD, silicon oxide, is not going to react anything. It's not going to react with the silicon oxide. So you just put it as it is in the furnace, and after the reaction, you just etching the metal. Then the platinum, which is sitting on top of this silicon, is going to form the platinum silicide, okay? And on the platinum, which is on top of this silicon oxide, it just remains as a platinum, like that. So that if you put this thing in the etchant, okay, wet etchant, then this platinum silicide is not going to be etched. Only this platinum is going to be etched, so that it has a self-aligned silicide. In other words, only the contact holes is going to form a silicon silicide, okay? And that's very much necessary for the modern devices, because the modern devices the contact holes are very small, very narrow. And we do need this self-aligned process. And that's why in most of the VLSI processes, they use titanium and cobalt. Nickel may react with other elements, so it's a very contaminant. So we use cobalt and titanium mostly. Okay. So why in modern VLSI gate itself is used as interconnection lines like a metal? Because the width of the gate is too small for metal contacts, as in the figure. And how? Thermal evaporation of trenchant metal on the silicon substrate. We use the evaporation because the thickness at this time is not that important, and that is the easy thing to do. So we do just the thermal evaporation and heat treatment for the silicidation and etching of unreacted metals, which is sitting on top of the silicon oxide and things. Okay. So this is the process. And then in a self-aligned manner, you have a titanium silicide like that. You can notice that we have a spacer here. And we have discussed about this, right? In anisotropic etching, in RIE etch, okay, for example, we can have this spacers automatically. We are not going to do the silicon oxide here. Now, in a silicide process, you have to have okay, let me go a little bit more detailed on this. When you form a interlayer dielectrics like this, and then in the modern devices, the gate length is sub-micron, is about 1 micron something. And the 1 micron is very narrow, okay? And then, as I draw here, if you form a contact holes on the gate like this, then this distance is less than 1 micron. And it's very difficult in lithography to define the width less than 1 micron. So we usually use this gate as interconnection lines. Okay, we do not form metals on top of this gate for another interconnection lines like this. It is very difficult. We have to use this gate directly as interconnection lines. So it is very difficult to define this contact holes on top of the gate, because gate already is very narrow, right? So what you do is in a silicide process, you deposit all the metals as it is, so that the metal is going to be deposited something like this, okay? In the silicide process, I mean. Then this also form a silicide, and then it becomes short. This drain and the gate or the source is going to be short with this side reactions of the metal lines on the wall of the gate, right? So it is inevitable, it is very essential to form a dielectric layer, silicon oxide layer, like this, to prevent the short. So this is the sidewall. We have to form that. And fortunately, to have this sidewall, what you do is, when you have a source and drain and gate like this, and then you deposit the silicon oxide, okay? silicon oxide to some thickness, and then the silicon oxide is going to be formed like this, right? And then you do the dry etching, anisotropic etching, so that these directions you have to etch this much, while for this you are going to etch only this distance. So this is very much thicker than this, so that after anisotropic etching, that is important, anisotropic dry etching in RIE and so forth, then this all etched away except this residues. We call that residues. So this is the way how to form sidewalls. It's just an automatic process. You don't need any mask for this. And then you deposit the metals, blank deposition. We call that blank deposition, and put it into the furnace. And then after the reaction, this oxide will prevent it to form a silicide along the side wall of the gate, so that it can prevent the short. Application of RTA process. The RTA, as you can see, this silicidation process, it just it just need a temperature for the reactions, and the materials to be for the reaction is not that much. A very thin film of platinum, cobalt, nickel, trench metals, and that thickness is several hundred angstrom only. Okay, so when those metals are deposited and you heat it up at 900 degrees centigrade or 950, then the reaction will happen in a minute. So, because the metal layer thickness is not that thick, the product, okay, silicide, is not going to be thick. Okay, it's about 100 angstrom or so. So, in practice, in the industry, they use RTA, rapid thermal annealing, for the silicidation process. Rapid thermal annealing process, they use a halogen lamp, halogen lamp, to heat up the substrate, and then this is the temperature profile that have been developed in my lab. Okay, as you can see, at the room temperature, it can go to around 950 degrees centigrade within 5 seconds. This is the temperature that you can of your sample. Okay, so within 5 seconds, from room temperature, it can be heated to the 950, and it stays there for 25 minutes of 25 seconds or so, and then just air cool it. And then with 30 seconds, less than 30 seconds is enough time for the silicidation reaction. So this is a very powerful. It's a clean process, and you don't have to spend the time to heat up your furnace. Okay, in the furnace, you have to spend a lot of time to reach 950 degrees centigrade from the room temperature. So the whole process is clean and simple, and this is a computer-controlled two-step process. You may need 700 degrees centigrade in the first time, and then you heat it up to the higher temperature for a short period of the time. So this is some kind of incubation time, and the preheating we call, and then this. And rapid RTA, the most important part is to kill the overshooting. Overshooting means if you heat up your sample too fast, then the temperature profile is going to so this we call overshooting. In order to reduce the overshooting, then this slope has to be slowed down. Then you can decrease the overshooting, but the time required to reach the temperature is long. So that is the drawback. But if you control the temperature with a computer, then you can optimize this temperature profile. Okay, so this is the results of the optimization of the heating process in our system. Well, let's talk about this problems and solutions. What time is it? 10 to 12. Huh? 10 to 12. We start on the 11th? Okay. I think we finish this lecture here, and then we pick it up from here in the next lecture. And probably we need next week, and then we need the 25th also for the lectures. Okay, I'll see you next week then.